Hello everyone, and welcome back to Revit Snippets. Great tips you can learn in just a few minutes.
This video is sponsored by Taggetize, the easiest way to run Tag All on multiple Revit views and sheets. Also, say goodbye to overlapping tags. Taggetize will turn this into this. Try Taggetize completely for free using the link in this video's description. This is the second part of my tutorial on how to model this dynamic facade pattern in Revit. In part 1, we already saw how to create the conceptual mass family. Then I also showed you how to create the curtain panel family and apply it to cover the entire mass surface. If you haven't seen part 1, just use the link in the video description to check it out. Today, let me show you how to write a quick Dynamo script to make these panels change their open ratio based on the distances to an attractor curve. To start, I'll now open Dynamo and create a new script. Let's begin with the first step. I start with a family types node where I select my custom curtain panel family. This lets Dynamo know which parametric panel we want to work with in the Revit model. Next, I connect that to an all elements of family type node. This gives me a list of all the panels of that family placed in the model. With this list, we can start retrieving geometric information about each one. Now we need to get the location of every panel. For that, I pass the panels into element.bounding box, then extract both the min and max points of each box. By averaging these, I get the midpoint of each panel. An easy way to get the average point of each box is by drawing a line from the box's min point to its max point. I can use a line by start and endpoint node to do this. Once the lines are in place, we can simply use a point at parameter node. Using a parameter value of 0.5, we can immediately get the midpoint of each box, as you can see there in the preview in Revit. With these midpoints in place, I can start to measure their relationship to an attractor. I'll select an attractor curve in the model using a Select Model Elements node. Make sure to select only the reference curve in the model, not the reference points on it. Then, I can pull its geometry using the Element Geometry node. As you can see in the preview in Dynamo, our panel location point and attractor curve are in the correct coordinates. This means I can use a new Geometry Distance to node to calculate the distance from each panel's midpoints to the attractor curve. By default, this node will use the shortest lacing mode. This is why we only get here one distance from the first panel to the attractor curve. To get one distance for each panel, simply set the node to use the longest lacing mode. These distances form the basis of our variation. To better use them to control the panel's openness, we need to reduce these distances to a list from 0 to the max distance difference. To do that, I'll first find the maximum distance using list.maximumItem. Then I normalize the values with a code block that subtracts each distance from this maximum. This gives me values between 0 and max difference, ready to be remapped. Now comes the important part, remapping those values. I will use a math remap range node, feeding in my normalized distances, along with two cutoff values of 0 and 1. These cutoff values act like thresholds, deciding which panels stay fully closed, which stay fully open, and which get rescaled in between. For a more simple script, this remap could have been enough. However, I want to have in this script a more custom range of open distances for the panels. To do that, I will need to use a bit of custom Python code, so let's add that to a new Python script node. The input to the Python node will be the list of remapped distances, along with two more custom cutoff values. The first value defines the lower bound of remapped distances. All panels that have a remapped distance below this value should be fully closed. The second value defines the upper bound of remapped distances. All panels that have a remapped distance above this value should be fully open. Let's take a closer look at the Python script node, which gives us more flexibility with cutoffs. I will edit it in Visual Studio Code, which is a much better coding environment. Before switching to Python, a quick shout out to our sponsor, Taggetize. With Taggetize, it's never been easier to tag multiple Revit categories at once using your favorite tagging styles. Say goodbye to spending countless hours untangling Revit tags. After running Taggetize on this view, for example, all my tags are perfectly readable. None of them overlaps with their hosts or other elements in the view. If I think this tag, for example, can be placed better, I can just select it and click Next to tell Taggetize to try the next possible tag position. Each time I click the button, Taggetize moves the tag for me, and I can keep doing this until it gets to a tag position I like. There we go. That's much better. Try Taggetize completely for free today using the link in this video's description. To start, I define a helper function called rescale2cutoffs. This function takes a list of values, a lower cutoff, and an upper cutoff. If a value is below the lower cutoff, it snaps to the minimum of the list. If it's above the upper cutoff, it snaps to the maximum. Anything in between gets linearly rescaled between the minimum and maximum. Inside the function, I first check if the list is empty. If it's an empty list, there's nothing to remap, so I can just return an empty list as well. If no min or max values are given, I infer them from the data. This is easy since Python already has helper functions for finding the minimum and maximum values of a list. I also compute the denominator for scaling, which is simply the range between the two cutoff points. The rescaling logic goes like this. If the value is less than the lower cutoff, append the minimum. If greater than the upper cutoff, append the maximum. Otherwise, calculate the scaled value proportionally within the range. Finally, I can set up the inputs and outputs. Values is the list of mapped distances. Range start is the lower bound, range end is the upper bound. Finally, I can simply call the method we defined earlier on these input values and then return the output back to the Dynamo graph. Back in the main graph, let's copy the Python code from Visual Studio to Dynamo. If you run this now, you can see the remet distances have been rescaled according to our Python logic. Before using these values to control the panels though, we need to put them in the right unit. This is because these values are now in feet, which is Revit's internal unit. My mass model is in millimeters though, so let's add a quick note here to convert from feet to millimeters. The converted values can now be used to control the openness of each panel using the panel parameter we created in the curtain panel family. If you haven't seen part 1 of this tutorial, that's where I showed how to add this open distance parameter. Using element.setParameter by name, I can assign each panel its corresponding open distance value. Make sure to supply the list of panels we got from the very start of this script. Also, make sure to spell the parameter name correctly, otherwise Dynamo won't be able to find the parameter to modify. Last but not least, remember to save your script and Revit model before clicking Run here. This operation can take a few minutes if you have lots of curtain panels, so if it crashes for any reason, at least you still have saved your hard work. The result is a responsive facade. Panels closest to the attractor curve will be fully open, while those further away gradually close, all the way to the maximum distance. What makes this workflow powerful is its flexibility. By adjusting the cutoff values or the attractor curve, you can completely transform the appearance of the facade without manual editing. I will prove that now by drawing a different attractor curve, selecting it, and then rerunning the script. As you can see, it's fast, parametric, and gives you full design control. Having said that, the facade doesn't look particularly appealing right now due to this dull gray color. To fix this, let's add a parameter to the curtain panel family to allow applying a custom material to these panels. I'll quickly open the panel family for editing and select all solid objects in here. Under the Properties panel, click the box next to Material and assign a new parameter to this box. Now when I go to Family Types, the parameter is available. Let's change it now to just a generic white material. At least that looks better than the dull grey one we currently have. I can now load the family back to the mass and select to overwrite all parameters. And there we go. The facade looks a lot more modern and clean already. Moving on, we need to place this mass inside a project model. After all, this is still just a conceptual mass family, so we can't annotate or schedule the panels in here. We need them in a project model to do that. I'll quickly create a new test project using the architecture template. Then, I'll go back to the mass family and load it into the new project. Feel free to place it anywhere that makes sense for you. For me, it will be here. I will quickly create a camera view here so we can see the facade from eye level. And that's it. We've built a facade driven by Attractor geometry using a combination of standard Dynamo nodes and a small Python function. Experiment with different curves and families, and you'll discover endless design possibilities. Before you go, check out our sponsor, Taggetize. Save all your tagging styles in one place and tag one or several views or sheets at once. Also, say goodbye to overlapping tags. Simply review generated tags and make any final tweaks with the handy tag audit commands. Try Taggetize completely for free using the link in this video's description. There's also a link in the description to download the script we built together today. Even more, if you want to master Python scripting in Dynamo to create this kind of script yourself, check out my full online Python for Dynamo course, also linked to in the video description.
If you like this lesson and want more like this every single week, make sure to subscribe to this channel now. For now, have a good day and I'll see you in the next tutorial.